In this video, we're going to talk about another very simple and very special type of network known as a random network, or an Erdős-Renyi random graph, after two of the mathematicians who are very well known for the research they did on understanding the properties of this network. This network is one of the simplest types of network you can imagine, and it's helpful to think about this network in terms of the way the network might be constructed. First, consider a set of entirely disconnected nodes like this. Then, all we're going to do is start randomly selecting pairs of nodes, like this pair here, and connecting them with an edge. Then we'll select another pair and connect them with an edge, and another pair, and so on. At first, this doesn't look much like a network at all. Technically, what we have is one network with many different and separated components. A component refers to a set of nodes that are all connected. Now, if you continue connecting pairs of nodes one at a time, this process demonstrates a very remarkable and regularly predictable property of random networks. As you connect the nodes, you see a sharp threshold. As the number of edges you've created passes this threshold, the graph is nearly guaranteed to suddenly become one single giant connected component. That threshold is defined in terms of the numbers of edges that actually exist as compared with the number of all possible edges. In other words, the proportion of all possible edges that actually exist. Let's call this proportion P. The threshold exists in this value P, and it's equal to log n divided by n. So when P is equal to log n divided by n, your network is almost guaranteed mathematically to be one giant connected component. This is known as the critical threshold. This graph has two properties that are very important for social science. We saw in lattice graphs that neighbors of neighbors tend to know each other, which is to say they have a fairly high clustering coefficient. If I lived in a lattice graph, my friends would all tend to know each other. That's due in part to the regular structure that creates the overlapping neighborhoods. However, in a random network, which has very little structure at all, it's very unlikely that two of my neighbors will know each other, since their neighbors are randomly selected from the entire population. And so a random graph tends to have a very low clustering coefficient. If you randomly select a node from a random graph and poll its neighbors, none of them will know each other. This property has very important implications for the social world. The second important property of random graphs is the average path length. In lattice graphs, if you randomly select two nodes that are far apart from each other in the grid that the graph is constructed on, it will require a lot of hops across each edge in order to connect one node to another node, which is to say, if you're trying to send a message from one node to another, one person at a time, it will take a long time for that message to arrive. They are very large graphs. However, in random graphs, the average path length between two randomly selected nodes is very small. In a very large graph, it often takes only a few hops to get from any node to any other node in the network. In other words, each node is just a few hops away from anyone else in the population. So which type of network do you think we live in? Do we live in a network or a world with very little clustering and everybody's close together? Or do we live in a world where our friends all know each other, but we're very far apart from anybody on the other side of the network? We're going to explore this concept more in the next video.